All right, we're on page 8. Yep, page 8 of the handout. We have a pulley with two weights, one, or I should say two masses. One mass is bigger than the other. The yellow or orange one is bigger than the green. What is the acceleration? Well, okay. Newton said acceleration is the net force, or the sum of the forces divided by the mass. Acceleration is determined directly by the net force and indirectly by the mass. So here's what we do. Once again, we've got to establish what's positive or negative. But we're going to do it something a little different. We're going to say that this clockwise motion, anything going in the clockwise direction, we're going to call positive. So we put that into our picture. And so what is the and we'll consider this as a whole system. What in this system is what force is acting in the clockwise direction? Well, that's big mg. What's working in the counterclockwise direction? Little mg. It's working the other direction. And the combination of these two, the difference between these two weights, difference between these two forces is the net force. Now, what is that net force accelerating? Not just m and not just little m, but it's accelerating both of them. And so we have the acceleration formula. We're going to make clockwise positive. We use Newton's formula to find acceleration, and that is the answer to the first one. Next question. Let's take a look at the next question. What is the tension of the rope on mass m? And, well, what's the tension on the rope? The little mass and the big mass. And here's something huge, that you should know, that this tension equals this tension. Because you're going over a massless pulley and it's frictionless, these two tensions are equal. So if I find the left tension, I have found the right tension. So let's see what we'll do. We can actually pick any of them. Let's see what this says. Yeah, this is what I said before. Here's the rule. One rope, one tension. One rope going over the pulley, one tension. So let's, even though if we find one tension, we find the other, let's get some practice. Let's isolate mass m and look at only the forces on mass m like we did before. It's very useful to isolate this one over here, and let's see what we can get. So there are two forces on mass m, the little m. So the sum of the forces equal ma. What's the positive force? Well, the tension is the positive force because it goes in the clockwise direction. So the tension is in the direction we call positive tension. Now the weight, little mg, that's in counterclockwise, and that equals ma, little ma, because these two forces are only accelerating the little m. So the tension, no surprise, is the weight and the accelerating force. So now let's do the other one. Big mass. Okay. There's big M, the big box with the big mass. Let's isolate that and look at only the forces on that box and ignore everything else. So what are the forces? Well, the positive force is, or the clockwise force is mg, which is positive force. Big mg minus t equals big ma. These two forces are only accelerating big ma. So let's undo that. Okay, so let's go down here. So what is the tension? The tension equals, we solve for t, mg minus ma. Hopefully it won't run out of room yet. Kind of running out. There we go. Mg minus ma. Sorry about that. I'll do it again. Tension equals big mg minus big ma. So these tensions are identical. That's why we call them both t. But this is in terms of big M, and this is in terms of little m. So we did it twice, even though we could have only done it once because those tensions are equal. All right, let's take a look at the next problem. You've got a hanging box. It's got more mass in the box than the table, and it's frictionless. The frictionless pulley, and I should have said it's a frictionless table too. So Fnet equals ma. Oh yeah, these two bodies will move just like the last two bodies. They both, here's something I should have pointed out. When this box is let go, they will accelerate with the same box. M will have the same acceleration as the big M will have the same acceleration as the little m. And that's true about this system as well. Once this big mass is let go, the acceleration of little m will be the same as the acceleration of big M. Let's establish our positive. Could have called that positive and this negative. So the two bodies move with the same acceleration, and Fnet equals ma. So let's take the whole system. What's the net force on this whole system? There's actually only one force because that's a frictionless table. So the only force on this whole system is a positive one. Big mg equals Fnet equals m. What m? Both m's are going to move. Both m's will be accelerated by that hanging weight equals a. And so the acceleration is the net force, big mg, divided by the two masses that are accelerated by it, and there you go. Big M, that's big M, and little m on the bottom. It's big M on the top. The only force accelerating the system, and it's accelerating both these masses. That's why that's on the bottom. All right, what would happen now? Here's an interesting question that people usually don't get right. If little m were hanging on the here, where big M is, if they just switch places, if the little m was hanging and the box was on the frictionless table, what would happen? A lot of people think nothing would happen. Actually, it wouldn't move at all because, well, the hanging box is less mass. That is not true, and I'll prove to it's not true because let's see. Hold on. Whoops. Here we go. So, right, lost my place. Here it is. Okay. If the smaller box were hanging, then the net force would be little mg. What would little mg accelerate? Both masses, m plus m. So when you solve for a, you get the acceleration depends on the net force, which is little mg. And what does little mg accelerate? Both masses, little m and big M. Okay. Now, what is the tension force? Now, same problem with the same acceleration. The acceleration, if this setup is, we're going back to the original setup where the hanging mass is the big one. So the acceleration is the net force, mg, divided by the two masses. That's little m and big M. Okay. Let's isolate little m right over here because it's the simplest one to do. It doesn't matter which one we do, but let's isolate this and simply say, what are all the forces simply on this one over here? All right, we were looking for this next question. We're looking for the tension. So we do an Fnet equals ma on the little box. We could have picked the big box, but looks like that's simpler, just one force. So the little box is the sum of the forces on the little box equal ma. Then let me get rid of this. The only force on the little box is T. T equals ma. And we already know from the last problem what a is, so we'll put the a in there. So T equals m times mg divided by big M plus little m. And that is the tension. I picked the one on the table because it has less forces on it. Find the acceleration if there's friction. What if there's friction on the box? Well, acceleration still equals Fnet over m. The positive force or the clockwise force, let's look back. The clockwise force would be the on the system is just mg. That's the clockwise force, mg. The counterclockwise force is the friction. And what is that? What is it accelerating? It's accelerating both both the little m and the big M. And so here's your answer for your acceleration. It is the hanging mg clockwise force minus the friction counterclockwise force. What are those two forces accelerating? Those two competing forces? They're accelerating both the little m and the big M. And that's all we'll do today.